So the difference here is that series motor. So in the series motor, I hope you know that the excitation is that is the field winding is connected in series with the armature. So that's the only difference. Remaining all things are very similar to the separately excited DC motor. Okay. So because of that, some torque speed characteristics will change, but the output of the converter does not change. So whatever the output of the converter we got in the previous class, same value you must get here also. Okay. So, so now you see here, we'll find out the output here. We'll find out the output here. Okay. So V naught, and these are the supply voltage waveforms, all the three phase, and the phase sequence is ABC is the phase sequence. Okay. So this is V naught. Then what we do is that, so everything is same like the previous class itself. There won't be much change except what is the type of motor it is. Otherwise, there is nothing else. Okay. So now you see here. So what you will get is that once again we will take we will give you, so semi-converter. I hope you know three thyristors are there and three diodes are there. Okay, and there is a freewheeling diode is there always. Okay, and then what we do is that once again we'll take the firing angle is zero. So if you take the firing angle is zero, then the ranges are from 30 degrees less than equal to omega t less than equal to 90. Okay, for this first 60 degrees duration, that is from this point to this point. From this point to this point, we have seen last class itself that phase A is the highest value, whereas phase B is the lowest value. Okay, then what we supposed to get is that VAB we will get. Okay, so something like this. So here, so VAB, so VAB, and this, so something like this you will get here. Yeah, this is the thing you will get. Okay, similarly from, so this I will write here. You want it is VAB, VAB. Then from 90 to one more 60, 90 to 150, 90 to 150. So 90 to 150. Okay, yeah, 90 to 150. Which voltage it is that you see yourself? 90 to 150 highest is VA, whereas the lowest is C. So VAC. So this way you can continue that. Okay, this way you can continue that once again from 150 to 210. 150 to 210. So well, its voltage is 150 to 210. Highest one is B, whereas the lowest one is C. So VBC. Similarly, from 210 to 270, 210 to 270. Highest is B, lowest is A. So VBA. VBA. Then 270 to 330. Highest is C. lowest is A, so we see A. So likewise, you can go ahead. So this is for firing angle alpha is equal to 0. So this is for firing angle alpha is equal to 0. Say for example, if you do the delay, if you do the delay, okay, if you do the delay in the sense, if the firing angle is other than 0, other than 0 in the sense, say from 10, 20, something like this, okay. So then in that case, what you find out is that in this case, what exactly you'll find out is that this delay, okay, this delay will be there here. This delay will be there, and the delay will come like this. And you know very well there is a freewheeling diode is there here. Okay, so the freewheeling diode will conduct automatically. Okay, okay, so okay, and then similarly, similar cases. This one. Okay. Okay. So likewise, so this is for alpha firing angle alpha firing angle. Okay. So then you can have further delay. You increase the delay. If you increase the delay, then we have seen last in case of the separate lecture DC motor, we have seen some waveforms that if you delay this further, like alpha is equal to 60 degrees, okay, then alpha is equal to 90 degrees, okay, then alpha is equal to 120 degrees. So three things we have seen. Just recall yourself that for alpha is equal to 60 degrees, what you find out is that this will come down exactly. So anyhow, we'll draw that here. Okay, see here. What do you find out here? When alpha is equal to 60 degrees, then the delay will be 60 degrees exactly. So when the delay is 60 degrees, then what you will find out here is that I will just show you here. From here, so 60-degree delay in the sense this entire 60 degrees will go, okay, will go out. It will go out, okay, something like this. Yeah. Then there is a sudden jump. Similarly, this will go. Which one? The next one. This one. So yeah, this one. Yeah, likewise. Likewise. Okay, let me do this also. Okay, this delay will be further. Yeah, then it jumps. So this you will find out. Okay, this is for 60 degrees. This is for 60 degrees. Okay. Similarly, if you go for 90 degrees, if you go for 90 degrees, what do you find out is that, uh, okay, let's see what you will get here. If it is 90, then this entire part, what will not be, this is also not there. Okay. Something a different waveform. Same thing, only that there is a delay is there, continuous delay is there. Then 0, then sudden jump is there. So this is the waveform. So it becomes 0 here, this duration. Okay. Similarly, yeah. Similarly, There is small duration, there the voltage is 0. Okay. Now you see that there is a delay here. In this delay, what do you find out is that your freewheeling diode will conduct. In this delay, the freewheeling diode will conduct. So this is for 90 degrees. Similarly, you can draw for 120 degrees also. You see, so in the 120 degrees, the delay will be more and more. Okay. So what is the observation you will find out in the 120 degrees is that this time the for alpha is equal to 120 degrees, it will enter into discontinuous conduction. So when it enters into discontinuous conduction, okay, what do you find out is that, I'll show you here. See this now. Yeah, this will be here. So the voltage is 0. Then here the current is 0. Then after this step, it will jump like this. So in this step, okay, let me complete this first of all. Okay, then, yeah, in this step, 0, voltage is 0, then current is 0. Then there is a step is there. Small step you will find out. Okay. Similarly, yeah, this you will find out. Now you see here in this part, freewheeling diode will conduct. What about this step is that this step is EB back EMF. Okay, because when there is no current here, then what is V naught? V naught is same as EB. This we have seen already. So this is all the four waveforms you will get. Okay. Once you got this waveforms, and what about the output voltage? V naught. V naught will be the same 1 by 2 pi by 3 integral 2 plus alpha to 150 plus alpha. VA minus VC, V of omega t with, yes. So then you do this thing. So the same equation. So if it's the same equation, then you must get the same answer. Like we have seen in the last class itself, 3 root 6 by 2 pi 2 pi into VL 1 plus cos alpha. Okay. This is similar kind of answer we got even in case of separately excited. Even in case of separately excited DC motor, we got the same answer. Just remember this thing. Just recall this thing that whether this is same or not. Okay, so you must get the same answer. Okay? So if you get this thing, then what about this? What about this phase angle relationship? What about the phase angle relationship? That V naught and alpha. Then something you will get. You put alpha is equal to 0, then it becomes twice. Okay. So then alpha you put 180, then you will get -1. So something like this. Yeah, you will get like this. This is the relationship between V naught and alpha. Okay. And similarly, you can find out the relationship between torque and speed. How do you find out the relationship between torque and, because we have this equation V naught is equal to EB plus IA into RA plus RF this time. And second thing is that what is EB in case of your DC series motor? Just recall yourself, K1 N plus K2 N phi. Okay, this you will find out. Then I can write this thing as because phi depends upon Ia. So I can further can be written as this as K1 into N plus K2 into Ia into N. This, you know. So this is because of the residual flux. Okay. You must understand there is a residual flux in case of DC series motor that we have seen even previous class also. Whereas this part is because of the actual field. This is because of actual field now. Okay. And then we have one more relationship. What is that relationship? Is that torque is proportional to Ia square in case of your series motor. So we will get Ia value from this and we'll substitute Ia here. Then that entire EB will substitute here. Ia also will substitute from this equation T proportional to Ia square. When you do all this shuffling, then you will get a relationship between speed and torque. So what is the relationship you will get is that I will tell you one important thing that I told you already, that the speed torque characteristics of your okay, your DC series motor is always like this. Whether it is single phase converter or whether it is three phase converter. Okay, this you will find out because this is a non-linearship you will get. So you go on increase the value of alpha, you will get this thing that this is the speed and this is the torque. This relationship you will get if you simplify all these equations. Okay, this we have done already in the previous cases of where you find out the series. There you can extract and you can get the here also. Okay, there is no other thing is there here. Then we will jump to the next thing is that we will jump to the same motor but full converter. We will see that three phase full converter fed DC series motor. So what is the circuit diagram? The circuit diagram will draw here. So you have all the six are thyristors. That's the only difference you'll find out. And there is no freewheeling diode unlike in the semiconductor. Okay. A, B, C. Okay, we'll do one thing. We'll copy this picture here rather than drawing once again. Okay, so we'll have this. Then so once again same procedure that it is 30, it is 90. So you will get something like this. Likewise, you will get in case of alpha is equal to 0. Okay, but when case of alpha is not 0, then what do you find out is that, okay, what exactly you'll find out is that there will be delay. So where do you find out delay? Delay you will find out here. So this you will find out when if it is alpha. So further, if you increase like that, then for example, if it is 90 or if it is some other angle, then this will increase further. Okay. So this kind of waveform you will get here further if you increase the values of. So the same analysis you will do even in case of your. What is the advantage here? You'll find out is that uh, V naught value is little bit different from the semi-converter. So you have seen even in the previous classes of your full converter, previous classes of full converter. That is in case of this separately excited motor. What is the expression you got in case of the separately excited motor? You must get a similar kind of expression here. Okay. So the expression which you got there, you must get the similar kind of expression here. Okay. Because your V naught value simply depends upon whether it is a semi converter or full converter. If it is semi converter, one expression. If it is full converter, you get another expression. And how it is different is that it depends upon which type of motor you have taken. Okay. So just recall that 1 by pi by 3 integration 30 plus alpha to 150 plus alpha SVB into d of omega t. So you will get this thing. So this is just a recall of the previous one. Ps cos alpha. Okay. This you will get. Okay. So then if you draw the graph between V naught and alpha, alpha is equal to 0, it is maximum. So this you will find out. Just it's a graph. Okay. So it is 180. It's 90. Okay. You'll find out like this. Okay. Yeah, what about the speed torque characteristics? Once again, I told you this is DC series motor. Whatever is the derivation, you must get like this. Okay. Because the derivation you will do here. Once again, V naught is equal to EB plus IA RA. You have one relationship, torque is proportional to IA square. This is one relationship you will find out. Now, in case of EB, you have 2 K1N plus K2 IAN. This is because of the residual magnetism. So using all these, you will get this graph. Alpha is equal to 0 and so on. Okay. So now, okay.